Tá, o que eu não fiz na última aula, que devia ter feito, é dar a prova completa, não sei se completa, mas pelo menos dar a construção do delta, que eu não fiz. Eu deixei em aberto, que o left-right functor de um funtor f, que esses caras, consigo construir um delta, tal que fica sendo um delta funtor. F é right exact. E eu deixei, na realidade, eu usei um lema que não provei, deixei para fazer a construção dele sem fazer. Então, vou fazer essa construção e, essencialmente, acabar hoje. Então, a ideia é a seguinte. Vou começar com uma sequência exata curta de objetos, A, B, C, a qual eu quero aplicar f, tá? Que é o que eu estou procurando. Estou procurando obter uma sequência longa que seja L0, F, C. Talvez devia começar por aqui. L0, F, C. L0, F, B. L0, F, A. L1, F, C. Esse que eu quero construir. E assim. Ok? Que eu disse, mas façam desse jeito e pronto. Mas tá, tem que fazer alguma coisa. A primeira observação é que neste caso particular, que é o zero, a gente sabe, isso já provamos, que isso é FC. Simplesmente pela exatidão à direita. Isso é FB, isso é FA. Então, procuramos o mapa de L1FZ. Assim. Ok. Então, como construímos isso? Então, agora lembremos. A ideia é pegar, que é só aí onde eu parei. Eu disse, tá, vamos pegar uma sequência, uma resolução de A, uma resolução de C. Essa é uma resolução projetiva de A, uma resolução projetiva de C. E aí a gente consegue, eu afirmei que temos uma resolução projetiva de B, fazendo que esses caras sejam uma sequência exata curta. Esses são os dados e esse é o existe. Que esses caras sejam uma sequência exata curta de complexos. Então, vamos supor que existe tal coisa. Tá? São resoluções projetivas com essa uma sequência exata curta de complexos. Mas, se eu vejo isso, então agora eu tenho para cada n complexos. Eu tenho de PAN para PBN para PCN. Esse é um complexo, é uma sequência exata curta. Logo, eu defino isso como um complexo acíclico. E são todos projetivos. Um complexo que é projetivo na categoria de complexos. Então, esse complexo é split exact. Isso provamos. Então, logo, esse cara é split exact. Isso vale para tudo n. Então, na realidade, aquela sequência era split exact. Ou seja, eu tenho um lifting assim. De PNC para PNB. E esse cara é a soma direta desses dois. Mas então, agora eu tenho uma sequência exata de complexos, que é essa aqui. que é split exact. Eu posso olhar, não, agora tem mais um dado. Então agora eu vou pegar f de P A para f de P B para f de P C 0, 0. E meu claim é que essa é uma sequência exata curta, de complexos. Por quê? Ou seja, está claro que para cada Pn, ou seja, eu tenho essa sequência assim. Se eu pego f de cada um desses caras, essa sequência é exata com certeza. Mas por que é exata? Essa sequência é exata de complexo. Exato. Obrigado. Então, essa sequência aqui é realmente split. Esse PB é a soma direta desses dois. Quando eu aplico o F, ele preserva essa soma. O F é aditivo, preserva as somas. Então, o F essa sequência aqui, que é uma sequência de complexos em chains, é exata. F preserva sumas. Sumas. Então, o F preserva cada uma dessas sequências, logo o F preserva todas as sequências. E agora, como eu tenho aquela sequência exata curta, eu tenho uma sequência longa associada a complexos, porque eu sei que homologia, e isso sim provamos, que homologia com delta é um delta funtor. Okay? Lembrem como que a gente construiu isso. A gente construiu esse delta utilizando o cone dos mapas. Mas do jeito, a homologia o que me dá é um mapa de o L, P, não, T, H0, F, P, dot, A, C. H1, F, P, dot, B, H0, 0, F, P, dot, A. Não consigo pensar com setas do outro lado. E esse daí vem de H1, F, P, dot, C, etc. Esse delta eu tenho de graça. E esse é o L, por definição, o L1F de C. E cada um deles é, contar. Esse é o L0, F de Z, o L0, F de B, etc. Okay? Isso constrói o delta. Bom, então, para construir esse delta, eu utilizei a existência desse cara aqui. Então, vamos construir esse cara. Okay. O que eu quero fazer? Eu tenho duas resoluções projetivas, eu quero ver que consigo uma resolução no meio. Tá? Eu tenho 0, A, B, C, 0, e eu peguei aqui um P0, que é sobrejetor para A. Eu peguei aqui um P1, um P0, perdão, C, CA, que é sobrejetor para C. E o que eu quero é construir um cara aqui no meio, obtendo ainda uma sequência exata curta. Okay? Bom, mas o que acontece? Eu comecei com uma sequência exata, curta. Então, esse mapa é sobrejetor aqui. Essa linha é exata. E esse cara é projetivo. Então, esse cara aqui existe. Existe um lifting desse mapa para B. Eu tenho um mapa de P0C para B. E também eu tenho um mapa de P0A para B, que é a composição desse lado. Ok? Então, aqui, obtenho um mapa da suma desses dois. Ou seja, a gente já sabe que o cara do meio tem que ser a soma direta dos dois, porque estou dizendo que eu vou ter uma sequência exata curta de projetivos. E que logo vai ser split, porque todo complexo projetivo exato split todo complexo que seja projetivo na categoria de complexos é split exact. Então já sabemos que esse cara aqui do meio tem que ser a soma desses dois. A questão é como construir os mapas. Então já sei que esse cara vai ser a soma dos dois, mas o mapa de esse cara para aqui é o seguinte: peguem um cara aqui, olhem para é a soma de um cara daqui mais um cara daqui. Esse cara daqui vai via composição e esse cara daqui vai via lifting, que eu escolhi. E aqui eu fiz uma escolha, um lifting. Tá? Essa escolha é arbitrária, mas eu escolhi. Então agora a pergunta é por que esse mapa é sobrejetor? Então, bom, olhem para o núcleo deste mapa aqui. Tá? Esse mapa é a aumentação do complexo A. Esse mapa aqui é a aumentação do complexo C. Então eu olho para o núcleo dessa aumentação. Eu olho para o núcleo desse aqui. Agora, esse aqui era sobrejetor porque essa era uma resolução. Então, essa sequência é exata. Essa é uma sequência exata curta. E essa sequência, pelo mesmo argumento, é exata. Essa era uma resolução, logo essa seta é sobrejetora. Então, agora eu peguei uma sequência exata curta aqui, uma sequência exata curta aqui. Agora, aqui eu não sei nada desse. Então, eu tenho aqui o conúcleo desse mapa. Esse vai ser a aumentação do B. Aqui terei o conúcleo do epsilon B. Okay? E aqui terei o núcleo do epsilon B. Tenho essas setas, aqui tenho essas setas. Okay? Mas o Snake Lemma me falava exatamente que essa ia ser uma sequência exata, que essa ia ser uma sequência exata e que eu tenho um mapa daqui para aqui, tá? Fazendo toda a sequência exata. Então, em particular, esse cara aqui é zero, e esse mapa é sobrejetor, e agora toda essa sequência aqui virou exata. Ok? Então, isso é o que o Snake Lemma me deu. Me deu um P0, agora eu tenho essa sequência exata por construção, porque eu pedi que esse cara seja a soma direta desses dois. Oh, I'm sorry. So this guy here is the direct sum of these two. So therefore, this line here is exact by definition. And now I am in this situation where this is an exact sequence, and I have these maps like this. So let's analyze our current situation. I constructed P0, B. And now I am in the situation where I have, well, I want to stop here. So this is surjective, and this is injective. Okay? So now I would want to continue by looking at, well, this kernel for this. Well, I want to construct P1. I have P1 that maps to P0. I have P1 that maps to P0 here, and I would want to construct a P1 that maps to P0B. Okay? So I have P1, what I have is P0A, P0B, P0C. I do have a P1 here, C, that maps here. I have a P, oh, no, I don't have this. I have a P0, P1A that maps here. And what I want is I want to construct a guy here. Well, I can do exactly the same thing as before. I can pick a lifting of this because now this map is surjective. And I can compose these two to get a map from P1B that I will declare it to be P1A plus P1C. But the choice of this lifting gives me this map like this. And again, I just repeat the same procedure everywhere. Okay? So at some point you might want to shift, because here what I did is I took the kernel of a map, well, the same thing you can do in that diagram. But it's exactly the same situation. You just go one row before. And this is, by induction, you end up constructing all of them. So step by step, you construct all the Pn's. And then since by construction, we constructed P, B, N as a direct sum of P, A, N plus P, N, C, we get that that sequence is exact, which is what we want. Okay. All right, so this proves that we have a delta. Now I don't want to do the next part. So now we need to prove that. I'm not sure if I want to do this. So I constructed this delta. So that came from the universal delta from homology. So now we want to check the following. We want to check that if you have a sequence A, B, C, 0, and you have another sequence A prime, B prime, C prime, 0, and you have maps this way, then you look at the long exact sequence. The long exact sequence is that, well, you have L, F, N, C, probably N plus 1 C, delta, L, F, N, A. Now these guys are functors, and this we did check before. So this maps to L, F, N, A prime. And these guys are functors. This maps to L, N, F, N plus 1, C prime. We constructed this as some delta. We want to check that this diagram commutes. But we did check this for H. So we did check that if we take projective resolutions, this happens. So, I'm sorry, not projective. We did check that if I have complexes, short exact sequence of complexes, and the functor instead of being this Ln, Lf is just H, this happens. So what we want to do is replace each one of these short exact sequences by a short exact sequence of complex that is quasi-isomorphic to each one of these objects. So that's by definition a resolution. So, and by what we just did, we can find split exact even, guys. So this is a projective resolution of A to a projective resolution of B to a projective resolution of C. Oops, C. And by the uniqueness, by the comparison lemma or whatever name I put, that whenever you have a map and you have resolutions, then you get maps between the resolutions. You get, this is A prime, maps like this. P dot B prime, P dot C prime to 0. And you have this diagram. Now this diagram happens in chains. But these guys are projective, so you can apply F to this. These are split exact sequences, so you can apply F to all of these guys. And this whole diagram commutes. And now you can apply H on this diagram. Now you apply H to this and use the fact that you have short exact sequences of complexes, short exact sequence of complexes. And by definition, you get that HF, HN plus 1 F of P dot C mapping to HF, HNF of P dot A. So this is the delta that the homology functor gives you. And this is the fact that homology is a functor. F P dot C prime. This is the delta that the homology functor gives you. N F P dot A prime. This is the fact that this is a functor. So this we get for free, and this is what we wanted to prove because this is the n plus 1 derived, left derived functor of f applied to C. And the rest is what it has to be. Okay, so that's this diagram. All right, so I think I've proven naturality that I said I didn't want to do. Okay. So that's all the abstract nonsense of, oh no. yeah, I did have some more abstract nonsense to do. And this is something I did in the examples last time when I computed pullbacks of shifts to the point. So let's do that. Let's prove that. I claim the following. So I analyze the functor. If you have R is a ring, a commutative ring, because I was talking about tensor product, so it's a commutative ring. Actually, no, let's not take it to be commutative. Let's do something slightly stronger. Let's say that R is an associative ring. It's not necessarily commutative. Then it's not true that I have tensor product of modules over R, but I can take a right module, let's say M, and I can take a left module, let's say N, and I get an abelian group, M tensor over R by N. So this is simply the usual tensor product over Z divided by the relation that MR tensor N is the same thing as M tensor Rn. Okay, so that's a tensor product. It's just that you lose the R module structure. If your ring is an algebra over K, then this thing is over K, and this is a vector space instead of an abelian group. Okay? All right. So typically, I'm going to be talking about rings are going to be algebras over a field, and this tensor product, this is a vector space. In the case that R is commutative, this is the tensor product, but this M and N are both bimodules, so you still have an action of R by multiplication. This is still a bimodule for R, where R acts by multiplication on the left on N and on the right on N, but this is just the same thing as having a module. Okay, so, but for associative rings, this no longer has an action of R. Okay, so suppose that I fix M, and I get the functor, which is the functor M tensor over R dot. And this is a functor that goes from the category of R mod to abelian groups. Yeah, I don't know how to call this functor, so probably Tm. But I also have this other functor, which is tensoring by N, which is a functor that goes from mod R. Did I do this exactly the other way around? This goes from mod R. So R acting on the right to abelian groups, and this guy goes from R mod to abelian groups. Both of these functors are exact. So this is tensoring by N. Both of these functors are right exact. Right exact. It's clear that they preserve surjections. Because, even though we've done this, if you have a surjective map from N to N prime, which is surjective, then you get a surjection like this by saying, well, just any guy here is a linear combination of vectors this form, and you can choose the preimage to be M tensor F inverse of N prime, because F is surjective. And this is clearly in the preimage here. So this preserves surjection, so this functor is right exact. So I can left derive it. Okay, so I can left derive the functor Tm applied to the module N. And how do I do this? Well, this we've been doing. You take a projective resolution of M in the category of R modules. M is a right R module in the category mod R. So this thing is computed by taking the homology of the functor Tm applied to this resolution. So concretely, you just take this complex, you tensor it over R with n, this is still a complex, and now you take the homology of that guy. On the other hand, I said you could left derive the other exact functor, which is tensoring by n, and that applied to M. So for that, you're going to pick a resolution of n. Oops. Now this resolution is in the category of R modules. And you compute this by taking the homology of the tensor with n of p dot n. What am I doing? Did I mix the m's and the n's everywhere? So tensoring with m, I took a yeah, I am mixing everything up, and no one is stopping me. Going too fast. The functor is tensoring by m. So if I want to apply it by n, I pick a resolution of n. This resolution is fine, it's in this one. It's just that by definition, it is my functor applied to the resolution of the object. That's the definition of this left-derived functor. And this is the homology of the complex, which is my resolution of n tensored by m. This is the applying my functor, which is Tm, to that resolution. Same thing here. I'm applying the functor tensoring by n to the object m. I need to resolve m. So I resolve it, and then I apply my functor, and then I take homology. But this is the same thing as taking the homology of the functor is just simply the tensor product over R. And now it's the resolution of M tensoring over R with M. And the statement is that these two things are the same. And the setting in which I've used it was by saying, well, I'm going to take one of my modules to be a ring. It's going to be an R algebra. And that this is the functor which was pulled back. So if I had R to S, which is an R algebra, or an R morphism, and you give me a module over R, this is sort of like a sheaf over the spectrum of R, which I can pull it back to a sheaf over the spectrum of S, which is just viewing that module as an S module. And for that, I take the tensor product over S. And I said I can do two things. I could either resolve the module, or I could resolve the ring. That's exactly what I'm doing. To resolve the ring, I didn't need to resolve it in the category of rings. I needed to resolve it in the category of R modules. In fact, none of the resolutions was in the category of rings. So the claim is that these two things are the same, and let's prove that, because we used that last time. And for this, this is sort of like the seed of the kind of problems that happen. So these are two complexes, and I do not know how to construct a map between these complexes. And you can't find a map between these two complexes. So what you can do is construct a bigger guy here that maps here, it maps here, and both of these maps are quasi-isomorphisms. So I'm going to find a complex with a map to this complex and with a map to this complex, inducing the identity morphism in homology here and the identity morphism in homology here. In that way, I'm going to decide that these two homologies are the same, even though there's no direct map between these two complexes. Okay? And I think this is the complication that one needs to solve when we move to derived categories. Okay, so, but you know what the guess is. I'm going to consider the tensor product of the resolution of M with the resolution of n. And this should be a complex. So this is a bicomplex. Let's check that this is a bicomplex. Okay. So I claim that this is a bicomplex. So let's do that. So if I put here P and I put here Q, and I'm very bad at this. So let's put P plus 1 and Q plus 1. Then there's a map which goes to P tensor. This is M, and this is Q plus 1, and this is N, and this is the differential on the resolution of M tensor the identity in the resolution of N. Or we can go down here to P plus 1 tensor over R. I should have used different letters for these P's. There's too many P's everywhere. P, P, P. There's a P here, P, and another P now. Okay. There's 3 P's in these things. Q. Again, this is just the identity tensor the differential. And, oops. And here I'm going to take PPM tensor PQ. And this is the identity tensor differential of N, and this is differential of M tensor identity. This diagram commutes, and this is on the nose. So if I grab something here, I apply the differential on the first factor. So let's start with something there. M tensor N. It maps to dm tensor N. Therefore, it maps here to M tensor dn. And if I do it the other way around, it goes to M tensor dn. And here it goes to, what did I do? I screwed up everywhere. So this is a dm that I had there, and it goes there. Right? So I apply a differential first on M, then on N, or first on N, then on M. It doesn't matter. Okay. So this is, I'm not sure if I define double complexes as things that commute or that anti-commute. So if I define them to be commutative, this is on the nose. If I define them to be anti-commutative, just put a -1 to the n here, -1 to the q perhaps here, and -1 to the q perhaps here. Well, q plus 1. In which ones? Did I take it on? Did I take it on? I don't remember if I took it on rows or on edges. Well, the way I'm doing this, I would put here a -1 to the p and a -1 to the p plus 1 here, and that certainly makes it anti-commutative. But this guy is commutative, is fine. Let's define the total complex of that bicomplex. So now, this we defined before. Once we have a bicomplex, we have the corresponding total complex. So we have this total complex of Pm tensor Pn dot. And the good thing about this complex is that it's well defined. It doesn't matter which. Definition. Remember, there was a subtlety when I defined this total complex that I said, okay, the degree n piece of this complex is going to be, it could be the product or the direct sum. When I take p plus q is equal to n, and it's going to be pmp tensor over r with pnq. And here it doesn't matter if I take sum or if I take product, because this is a finite sum. Right? There are finitely many guys because both of these complexes are in chains that are bounded below. Okay? Either in R modules or in mod R. So this double complex there lives in a quadrant like this, and these are the total ones. So this is the total complex 0. It's just P0 tensor P0. The total complex of degree 1 has two summands. The total complex in degree 2 has 3 summands, and so forth. Okay, so and this complex is supported on this quadrant. So this sum or this product are the same thing. This is the complex, and what is the differential in this complex? Well, is the differential here. Let's add the multiplication at this stage instead of adding it here. So the differential on tot n is so the differential of some m in this resolution in degree p tensor n in this resolution in degree q. You define it to be dm tensor n plus minus 1 to the q times m tensor dn. And this thing was in degree p plus q, when this thing here is in degree p plus q minus 1. Okay? So that's a total complex. And the claim is that this thing here maps here and maps here. So tot of the tensor products maps to this complex and maps to this complex, and so I have two claims. This maps here, and both of these maps are quasi-isomorphisms. So let's prove that. Well, yeah, I can probably redo this here. So this is, now that we know that our complex lives in this first quadrant, and I have here, sort of like kind of sucks to have PMs. Can I switch to M0, N0? Can I switch to something like this? M0, N0? And this means, yeah, let me call the resolutions M dot mapping to M and N dot mapping to N, so that this complex is N, N0, N1, and so forth. And let's not use any more P. So let's remember that these guys are projective, and that's the only thing we need. So I have this guy here. So this first row is going to be M1 tensor N0, N2 tensor N0, and so forth. And the differential goes in this direction, and this is the only differential. The differential goes in this direction, and there's no differential in n because there's no n minus 1. Okay? In this column here, on the other hand, I will have M0 tensor N1, and the differential will go vertically below. So here I'll have M0 tensor N2, and the differential will go in this direction. And there's nothing in that direction because I don't have an m minus 1. Okay, but I do have here two components of this differential. So if I take this guy that I have M1 tensor N1, one component would be in this direction, and the other component of the differential will go in that direction. Okay? And so forth. So here I would have M2 tensor N2, N1, and I will have this component, and so forth. All right, so the claim is that, well, I could put here the complex. You see, I have M0s everywhere here. So here, I could put the complex M0 tensor N. Right? And I have this map here. Because N0 maps to N, and I can tensor that thing with M0. Okay? So here I have M0 tensor N1. Oops, no, sorry. What did I do wrong here? This is all N0s. No, this is the other way around, actually. So the arrows in this direction go from M2, M1, and M0. So here I could put M tensor N0. And I'm using the map from M0 to N here. And the same thing here. I'm using the map from M0 to M, but now this whole row is tensor with N1. And the same thing here. I have M tensor N2, and I have these maps like this, and I can extend this like this, and of course I have these maps like this, and at the bottom here I have M tensor N, which is the actual object that I want to derive. Okay. So the complex is the total complex is here. It doesn't see this column. The total complex stops there, right? But the claim is that this total complex is mapping to M tensor the resolution N. So this arrow there is a map from tot of the tensor product of these two guys, and it's mapping to M tensor N dot. And this is a complex, this is a complex, and this is a map of complexes. So let's check that, okay? So I just need to give you what is this map, which I claim I already told you what this map is. So the total complex here in degree N, well, let's write it there. No, I don't want to continue there. I have the graph. Let's just point it in the graph. So I'm going to look at the total complex in degree N. So let's say here is degree 2. So I have this guy, I have this guy, and I have this guy. And of course, this is a line that is some diagonal like this. This is the total complex in degree 2. And I want to land in this guy in degree 2, and I have a natural map here, and all of these guys I send to 0. So I'm going to send whatever I have in the first column to the corresponding guy in the side, and everything else in the diagonal is going to go to 0. Okay? So I grab my total complex in degree N. This is Mn tensor N0 plus Mn minus 1 tensor N1 plus the last guy is hopefully I didn't screw this up, exactly the opposite of what I want. Yeah, of course I chose the opposite of what I wanted. So the last guy here is M0 tensor Nn. And I want to land in M tensor Nn. So I want to land in M tensor Nn. So I'm going to send all of this to 0, except this last summand. And in the last summand, I'm going to use the augmentation of the resolution. Remember that I started with the resolution like this, tensor the identity in Nn. So this is my map. So now I claim that this is a map of complexes. So I just gave you a map from dot N to the complex M tensor N. So this goes to the complex M tensor N dot in degree N. And I claim that this is a map of complexes. So I need to take the differential and then map, or map here and then take the differential. But then probably we can see it here. It's probably better, right? So if I am in an interior node and I take the differential, right? So anything that is below this column, when I apply the differential, I'm not going to reach this column here. So when I apply the differential and then I map, I'm going to go to 0. And if I first apply the map, it's already 0. So when I take the differential, it's 0. So the only things that could contribute are things that are in this column or this column. Okay? So in the first two columns are the only things that could actually contribute. So, well, let's see both. If I am in one of these guys and I take the differential of this, the only differential is the vertical one, and I land here, and then I apply my map, I land here, And if I do it the other way around, I apply my map, and then I take the differential, I land in the same place. Right? So this diagram commutes. This was the fact that I had a double complex. So that's fine. So from here, from the first column, I just check that this thing commutes. Now, how about in the next column here? In the next column, I can apply the differential and then map, and I would land here. And then I miss this part of the differential. Okay? Now, if I map it from here, I'm sending it to 0. So what is the problem? So if I map from here, I'm going to get to 0. Then I apply the differential, is 0. The only problem is that if I apply the differential and then I map, this composition was 0 in my complex. So this was a differential in the complex, and this is the augmentation in the complex, and it was defined in such a way that this guy was exact. So if I apply the differential and then I map, I get to 0, 2. So this is a map of complexes. Okay, so we checked that we have a map of complexes. So now I want to check that this is a quasi-isomorphism. So that's one claim. Of course, you also get a map of complexes in the same way by sending the first row to the -1 row that I'm going to take it to be the resolution of n. So I'm going to map from here to m, what the hell, m0 tensor n0, no, tensor n, then m1 tensor n, and so forth, m2 tensor n, and the map is going to be the augmentation of the n resolution tensor the identity on the corresponding m. So that's going to give me a map of complexes in the same way to this complex, m dot tensor n. I don't have a map here, but this map is also going to be a quasi-isomorphism. So I want to check that. Okay, so let's check this. Okay, so let's take the lemma is the following lemma. Let C dot dot be a double complex and let's suppose this dot here is bigger or equal than 0. Yeah, I'm almost guaranteed to get this wrong. But if the rows are exact, I'm mostly guaranteed to get rows versus column wrong. But anyways, if the rows are exact, then the total complex is exact. I think I'm going to get something wrong. But anyways, let's just try to prove this. And if we fail, we're going to find if we failed. Okay, so this is saying that I have a complex that has 0 below this diagonal. It has some things above it. And the rows of this complex are exact. Did I screw this up? Well, no, I don't know. So this is going to be some degree of this complex. This is some degree n, and the differential goes to degree n minus 1. So the differential on this complex goes in this direction, and below in this direction. Okay? So let's suppose that, so I want to prove that this complex is exact. So anything that is in the kernel of the differential, I want to find something in the in the image of the previous differential. So I'm going to start at this point. And I ask what is in the kernel of this differential. But the only thing that I can have in the kernel of this differential is only this differential. And I'm assuming that the rows are exact. So anything that is in the kernel of this differential is in the image of this differential. So it is exact here. So now I come here. And I ask what is in the kernel of that differential. But now this is a problem because this is something that if I apply D, I'm going to get something here and something here. And I'm claiming that these two things are 0. Right? So the sum of these are things in different spaces, and these two guys are 0. So now I need to construct something that would kill me this guy. Okay, so how do we land here? Well, I can take something from here and something from here. So I need to construct some combination here that would kill this differential there. Is it clear? Okay, so I want to construct a guy here and a guy here such that when I take the differential, well, this d of this goes here, d of this goes here, and d of this goes here, and d of this goes here, and I would want to have it in such a way that I kill whatever I had in the kernel of the differential here. Okay? So I hate these kind of things. I can't see these things in the board. So what do? Well, since this guy was 0 here, there is something here that maps to that guy here, because this guy was exact. This row was exact. Okay? So I had something that when I applied D, I got the sum of two things, but then this guy was 0, so there's something here already that kills it. So this smells fishy. I'm constructing something already in 1 degree less, so what's wrong? What's wrong? Can anyone tell me what's wrong? Certainly here it's fine. The differential of this guy being 0, it's in the image. What's wrong at this point? Okay, so the things that these things might not be homogeneous. So, right. So what I'll do is I need to take a guy in the sum in this diagram. So I need to take a sum of things that are of the form B VP tensor W n minus p, where these are the degrees of where these guys live. Okay, so this guy here, well, it's not tensor. I should say this in a different way. Let me put this as VP. These are not tensor product. These are just a bicomplex. So this is n minus p. And this goes from p is equal to 0 up to n. And this guy here, VP n minus p, lives in C P n minus p. So the typical element of the total complex is a sum like this, or a product if I'm looking at the product of guys like this. And now I need to take the differential of that and ask to be in the kernel. The differential of this thing, well, now this is going to be a sum of differentials. Okay? So the differential, let me call this guy V. And this guy is 0, but the differential of that guy in degree, well, this is in degree n minus 1. So this is in degree p n minus 1 minus p. What is that? Well, this is a sum of two things. Right? So I'm grabbing the sum of guys, and I'm asking what do I have in the differential here. So this is the differential of what I had here plus the differential of what I have here. So this is the differential of the V p plus 1 n minus 1 minus p plus or minus whatever the sign is the differential. This is the horizontal differential and this is the vertical differential of the Vp n minus p. And I'm claiming that this is 0. Okay, so now this has a little bit more sense. So now I'm looking for some linear combination of elements that give me these guys in these degrees. So I got each one of those for here. I claim that each one of these guys is 0. Therefore, now I'm looking for a linear combination here in this diagonal that map to my original linear combination before. Okay, so still. Okay, so I presume that we can do this by induction. Right? I can. Right. Right. So we can do this by induction. So as I said before, we start at this point. The differential of this is 0. Therefore, we find something here that maps to that. Now, it's true that this guy here would go to 0. Therefore, I can find something that goes here to 0. But the problem is that the differential of that guy may screw up what happens here. Right? So if I constructed already this. Now I want to construct this guy. Now, if I just take it as something that maps to here that is given because this guy went to 0 here, then the differential of this alpha 1 would contribute something back here, which is not what I originally wanted. So now I need to correct what happened here. Now, I grab my alpha 1 that I construct, and it exists that kills whatever I have here by this horizontal differential. But then I take d vertical of alpha 1, and d horizontal of that is 0, because this went to 0. So that means that the d vertical of alpha 1 here is in the kernel of this differential. So I can also find something here that corrects that. Let me call it delta alpha 1. So now when I apply the differential of this, still the square kills the same guy, because this guy was in the kernel here. But now the differential of this plus the differential of this, well, probably minus, is 0 here. Okay? So I didn't change that situation. Is it clear, or should I spell it out? Should I spell it out? Oh. Okay, so what is this position? This position is the position Cn0. And I'm looking for my component is Vn0. And the differential of the Vn0 is the horizontal differential of Vn0. And I'm claiming that is 0. So the first step of this induction is that I hate these kind of things. The first claim of this induction is that there exists some W n plus 1, 0, such that the horizontal differential of W n plus 1, 0 is equal to Vn0. And this happens because the horizontal rows are exact. So this is horizontal rows are exact. So we have our Wn plus 1, 0. So now we look at what happens at this point here. This is my V n minus 1, 1. And I look at the differential of this. Well, this guy has a component. Oh, shoot. I'm doing this wrong. And no one is stopping me. Why you guys are not stopping me? I hate this. This wasn't 0. And this doesn't need to be 0. no, I can't, right? Because so this plus this is 0. That's what I can suppose is 0. Because whatever I got here is 0. So let's start there. Holy shit, I'm horrible. I'm really horrible. Yeah, so I cannot assume that this is 0, because what I know is that the component of this guy here plus the component of this guy here is 0 here. That's the only thing I know. So let's put those names. So the horizontal differential, the vertical differential of some Vn minus 1, 1, plus the horizontal differential, and I'm not going to care about signs, of Vn 0, I can claim that this is 0. So I'm looking at the kernel of the differential on this diagonal, and I'm looking at the component of degree n minus 1, 0, the bicomponent of degree n minus 1, 0. So this is 0. And now I'm looking for a way of killing the part that comes from here and some part that comes from here. Okay. So what am I going to construct? And perhaps I want to use that the columns are exact instead of the rows being exact. And perhaps this is my problem. Perhaps I'm never going to find this way. So if the columns were exact, I can certainly find something that maps to this. Let's see, what the hell? Horrible at this. Yeah, am I going to find this? Perhaps I'm never going to find it this way. Yeah, perhaps I want to use that the columns are exact. But anyways, maybe I want to use that the columns are exact, because, or if it's a sum, saying that there's one last one that is zero, that is non-zero. So I think the way I phrase it for the product, I think I want to use that the columns are exact. You see, the problem here is this, is if I know that the columns are exact, I can always find something that kills this guy, or probably this guy. But otherwise, I need to start. So let's say that I took the total complex with the sum instead of with the product. So if it is with the sum, then on this diagonal, I'm taking an element whose differential is 0, but there's a last one that is non-zero, because it's a sum. I'm not allowed to take a sequence that is infinite and is non-zero on every point in the diagonal. So there's a last one here whose differential is 0. A last one here such that everything else is 0. So let's assume that. So I have this last one here whose everything on this side is 0 here. And now I take the differential of that, and this has to be 0. The point is that if this guy is the last one that is non-zero, to this differential, this is the only guy that contributes. And I can start here instead of here. So now the differential of this has a component here and a component here, but this guy has to be 0 if the total differential was 0, because there's nothing here that could have come. So this guy, the horizontal differential is 0, And since the horizontal rows are exact, I can find something here. Okay, this one works. So I can find something here that maps to this guy, right? Because the horizontal differential of this guy is 0. Okay, so now I look at the vertical differential of this, and what I know is that the vertical differential of this plus the horizontal differential of this is equal to 0. Okay? On the other hand, what I know is that, well, I can just look at the vertical differential of this object and apply the horizontal differential of whatever I get there, and I claim that this allows me to construct something here. So if we do this, then we continue by induction. Okay? So let's write that out. So I think that was the biggest mistake. So the proof goes along these lines. Let V be the sum of V n P Vp n minus P. And this is a sum. So P is bigger or equal than something. So I'm not allowed to take negative P for too much. So P is bigger or equal than some n might be negative. So that this guy becomes larger and larger, that's fine, but it cannot go whatever. So I am assuming that, let's say that n is the first one that is non-zero. And everything else is 0, right? Because P is bigger or equal than. So that's the setup. Let's take d of v is equal to 0. So now I'm going to look at the component in degree big N minus 1. V. I claim that the horizontal the differential of v n n minus n, the horizontal differential is 0. So that's the first claim. And this is because this guy lives in C n minus 1, n minus n, and the images of the total complex that land here are either C n minus 1, n minus n plus 1, and this V doesn't have a guy here in this component. N was the lowest one, such that V had no component. So in n minus 1 I have nothing. And the other one is V, which is C n n minus n, which is where my V, this component lives. So this means that there exists some W n plus 1 n minus n such that the horizontal of W is equal to V n n minus n. Okay, so we started at the top, this one was 0, we constructed this guy that kills this. Okay, so we killed something. So now I look at so now I would want to look at my V, but I want to subtract the total differential of this W. This W was in degree n plus 1, n minus n. Is the differential of this equal to 0? That's probably not true, because I am taking out this differential. So I took out this piece that I had before, but I'm also subtracting something here. Okay? So now the differential of that difference is the differential of V, which was 0, plus this differential. So what is the differential of this thing? The total differential of this minus the top of W n plus 1 n minus n. Well, this is the total differential of V, which was 0, minus the total differential of something. So this is 0. Okay, the complex is a complex, so the total differential square is 0. So this is an object that has d of this guy is 0. Took a long time, I'm sorry about this. But this guy here has no component, has components, the sum of p bigger or equal than n plus 1. Okay? In Cp, well, Cp n minus p. So now I can do this by induction. So I started with something that had n non-trivial components, and now I have one less non-trivial component, and the differential is still 0. So by induction, I can claim, I can claim, or I can reduce to the case where I only have one guy, which is in degree 0, to the bottom row. And in the bottom row, I use that row is, so I started with something, this one, the last one, I killed this last, I constructed another one in the same diagonal, whose differential is still 0, but this one became 0. So now I make this guy 0. I make all of them 0 except this last one, and this one I can do because this row is exact. Okay, this works. What would have been much, much easier is to prove without the condition of the sum, but put that the columns are exact. So let's do that. So let's look at what happens if the columns are exact. So if columns are exact, yeah, I'm sorry, I'm completely illiterate for these things. Can't look at these diagrams in the board. So now this is the bottom row, and I'm going to suppose that the columns are exact, and I'm going to grab some guy here whose differential is 0. So, well, the differential of this is 0, so it doesn't matter. Let's look at this. The differential of this guy is something here plus something here. So this is, and the differential of this is this, which the differential of this here is 0. So, yeah, okay, so we can play the same game just starting from this guy now. So what I want is to make this guy 0. So I'm going to make this time I'm going to start here, and I'm going to make this guy 0. Okay? This map here is surjective. So I can choose something that maps to this element here. So I take this guy, right? So I have this element here. I choose this alpha here. My v was spread over this diagonal. It could be infinite here. This is my v that has infinitely many components here. It doesn't matter that guy. But the point is that I choose this alpha who surjects into this guy. And now I look at my v minus the total derivative of alpha. And same argument. Minus the total derivative of alpha, d of this is 0, because d of v was 0, and this was the total derivative. And on the other hand, the derivative of alpha killed this guy. So this object here starts in this row and goes up. So this way you kill everything in this is going to produce an infinite sequence that is going to kill all of the v's that you have here. But it's an infinite sequence. So this never stops. Okay, so exact columns allow me to get a total exact complex for the product, and exact rows allows me to get a total exact complex, but only for the sums. Okay, yeah, we got that right eventually. Took a long time, but we got it right. Okay, so now I need to claim that we have both. So let's look at our situation with the tensor product. So what is the situation with the tensor products? So I had the resolution for M. I took the resolution for N over R. And this guy, by using the m augmentation. So I added, I think I was doing this for m or for n. Yeah, I suppose it's fine. So by adding the n augmentation and the identity on the n complex, I'm using lower indices. This maps to m tensor n. But now look at this. So this, I claim that these guys, this augmented complex, has exact rows. Okay? So the complex, the total complex, the bicomplex, the tensor product, did not have neither exact nor exact columns. But once I augment it to m, does have exact rows. The same thing for the for m itself. So the complex m is not exact, the resolution, m0 to m1 to m2, etc. This guy is not exact. The homology of this guy, by definition, in degree 0 was m. So if you augment it to m, this guy becomes exact. Okay? So now, the point is that all of these guys were projective, and tensoring with a projective is exact. Well, with flats. So now this allows me to say that this complex, this extended complex, is a cyclic. So that means that this guy here is a resolution of this complex. So this thing here with this augmentation map is a resolution of this complex. So that means that the homology of this complex is the same as this complex. So this is a quasi-isomorphism of complexes. So I get that this 2 m tensor n dot is a quasi-isomorphism of complexes. In other words, this is a resolution of this complex. This is a resolution of this complex. Okay? Okay, so the extended complex total extended by this is a cyclic. That means that this is a resolution of this. That means that the homology of this, which is the homology of the total complex, is the same as the homology of this complex here. And I have a map from here to here. I also have a map the same way from here to m dot tensor n, with same argument. Tensor n. This is the augmentation of n, tensor the identity on m dot, and this is also quasi-isomorphic. By the same argument, because this complex here has both columns and rows that are exact. Well, if you augment it this way, the rows become exact. If you augment it this way, the columns will become exact. So then you get the two quasi-isomorphisms. So this means that the total homology in degree n of the total complex of this tensor product is the same as the total homology in degree n of m tensor n dot, which is the same as the total homology in degree n of m dot tensor n. And this thing here was defined to be the left-derived functor of tensoring with m applied to n in degree n, and this was defined to be the left-derived functor of tensoring with n in degree n applied to n. So these two things are the same. So since that thing doesn't change, it doesn't depend on which resolution you take, I'm going to use the notation. I'm going to use the notation M left derived N to mean either of them. So this means a complex whose homology is either of them. It's either this guys or that guy or whatever, all of them. So in particular, it's quasi-isomorphic to this complex. The total complex for this, or M dot like this, or M, oh shoot, or M dot tensor N. And I need to mean what I mean by that these are the same. So when I write this, I'm thinking on either of these complexes, but this is tricky because I am writing isomorphism here. I'm writing isomorphism here. But I don't have a single map between these two guys. I only have a map from here to here and from here to here. And I don't have a map from either of these to this guy. So what do I mean by this isomorphism here? So from now on, and this is what we want to justify, is we want to invert, to consider two complexes that are quasi-isomorphic as isomorphic. And this is going to be tricky, so that's what we're going to do next. So the situation that we have now is we cooked up a bigger complex. So I wanted to compare two complexes, C1, let's say C with D, and I cooked up an E with a map to here, with a map to here, and this guy was an isomorphism. So I will look at this diagram, and I would say, okay. So whenever I have something like this, I will declare that I have a map from here to here. So whenever I have, so there might not be a map of complexes from C to D. And I'm not allowed to invert. So these two complexes might have the same homology, but there might never be a map between these two guys. Now, if I am in a situation like this where I find a complex with maps here and maps here, such that these guys are isomorphic, are quasi-isomorphic, then I would say, okay, fine, then I want to consider these two the same. What's the problem of considering these two the same? If I have two complexes and I say, well, not only they have the same homology, but I have an actual map that realizes that isomorphism in homology. So having a quasi-isomorphism means I have a map of complexes from here to here that realizes this isomorphism in homology. Okay, so I want to declare that these two complexes are the same. But then I'm in trouble, because if these two complexes are the same, a morphism from here to here should be the same as a morphism from here to here. So if I declare these two are the same, then this should be a morphism from here to here. Okay, so then we add these morphisms. So I'm going to cook up a category where these morphisms actually exist. So I'm going to declare that this is a map from C to D. And now I'm in trouble, because now what happens if I have a map like that from C to D, meaning there exists an E and maps here, and this is a quasi-isom. And now I have another map from D to F, meaning there exists some G here with a quasi-isomorphism like this and a map like here. Then I need to construct a map from C to F, because if I am in a category, I need to get the composition of these two maps. And to get this map, what I need to do is I need to construct something, H, that maps to C, that this is a quasi-isomorphism, and that maps to F. Because this is the notion that I have now of maps. So how do I construct this H? Well, if I could find a map to E such that this is a quasi-isomorphism and this comes with a map to G, then I could just take that. if this is a quasi-iso and this is a quasi-isomorphism, this composition is a quasi-isomorphism, so that defines this arrow. And now the map to F is just this composition. So this works. The problem is that this guy does not exist. So in general, this guy will not exist unless I start identifying things. So what's going to happen is that we are going to consider the category of chain complexes. And the first step we're going to do is map to this category that I already defined, where the morphisms are not maps of chain complexes, but so the homes in here, where maps of chain complexes divided by homotopy equivalences. This we check that you could compose them and that you get a category that is no longer an abelian category. Now, in this category, we're going to be able to invert these things. And so you're going to be able to define all of these maps modulo this relation. So these maps do not exist on the nose, but they exist modulo a chain homotopy. So that's what I'll think I'll do next time. But today, yeah, so today is what? So next week I'm not here. So I think the next, yeah, so next week there's no classes unless you want to have classes on Friday. Next week I'm not here, so and the other week I'm here only on Monday. So I think next time is the other Monday, unless you really want to have classes.